Hello again. This is Math 2231 coming to you from the College page, and the title of this lecture is LSA solution, and the one we're talking about here is the limit as n goes to infinity of the nth root of n is equal to 1, and we're doing this without using L'Hopital's rule. As always, please be attentive when watching these videos. If we start just with a little bit of empirical exploration, we can look at numerical values, and we can see that as n gets big, running from 1 to 1,000,000 by orders of magnitude, the number that is calculated here, n raised to the 1 over n, gets closer and closer to 1, and so we can suspect that the limit does exist, but we have to prove that it exists, and that's what our task is. So let's begin. So let's observe that n raised to the 1 over n is bigger than or equal to 1 for any n in the positive integers. So that is 1, 2, 3, and so on and so forth. Next, note that for x greater than 0 and n a positive integer, we have a thing called the binomial theorem. So we can actually expand 1 plus x raised to the nth power. And so 1 plus x raised to the nth power is going to be the summation from n equals 0 to n of, this is the binomial coefficient, n choose k times x to the k. And this actually is true for x not having to be greater than 0, but we're using it. But later on, we're going to use the fact that x is greater than 0. So anyway, we then do this. Now, these binomial coefficients, we know formulas for these from your pre-calculus class. And so we have these formulas. But now, since x is greater than 0, all of these terms are positive. And so we have a whole bunch of positive terms here. But in particular, when k is equal to 2, this is going to be n choose 2 times x squared, and n choose 2 is n times n minus 1 all over 2. So you see what happens is when we expand this using the binomial theorem, we get a bunch of positive terms and this thing which is also positive. So that means that this left-hand side must be bigger than that because we're adding positive terms to get that. So we can conclude that 1 plus x whole to the n is bigger than n times n minus 1 over 2 times x squared for all or any x squared bigger than 0. And we're going to make a clever choice. Let's pick x to be the square root of 2 over n minus 1. And this certainly is bigger than 0 because that's the principal square root. So then what we can do is we plug that into this equation for x. Now on this side, when you square that, the n minus 1 and 2 both cancel and you're just left with n. And on this side, we let x be the square root of 2 over n minus 1. And we're raising that to the n. So you see this is bigger than n. So now what we can do, since the nth root function is order preserving for positive numbers, we can take the nth root of both sides. Now when we take the nth root of this side, we will have 1 plus the square root of 2 over n minus 1, and that has to be then bigger than n to the n raised to the 1 over n power. But we already know that this is bigger than or equal to 1 here, and so we have a situation that conjures up the squeeze theorem. And note the squeeze theorem certainly can work for n going to infinity. And so that means that this is caught between 1 and this goes to 1 when n goes to infinity. And so that says this limit does exist by the squeeze theorem, and in fact it's equal to 1. Kind of an elegant proof. But an epsilon delta approach is also possible, and I think it's instructive. And I would encourage serious students to ponder this approach. And we begin here by noting something, and that is that if we let y equal the limit we're trying to compute, then if we take the natural logarithm of y, this 1 over n in the exponent goes in front, and we can use the continuity of the logarithm function to conclude that the natural log of y, the value we're seeking, is the limit as n goes to infinity of the natural logarithm of n over n. And you want to make sure you understand why you can do that. There's a couple of things going on, the continuity as well as properties of limits. Okay, so you see, if we were able to say that the logarithm of y, which is this limit um, of that ratio, is equal to 0, then by the log inverse properties, we could say that means that y is equal to e to the 0, which is 1, and we would be finished. So let's see if we can do that. In fact, let's do that now. Okay, so we start looking at this ln of x over x, and we are going to be trying to show that the absolute value of this minus 0 is less than epsilon. But first we're going to note that this absolute value of ln of x over x is less than or equal to the absolute value of 1 over the square root of x. Now, and it says you should check this. I did check this kind of for you, and I had to graph these. Now, this is a little bit technical, but here is the square root of, it's 1 over the square root of x is the blue curve. The red curve is the one that we're looking at. This is ln of x over x. But you see that that's negative for some of these values, anything less than 1. And so you have to deal with that a little bit, and so we will be dealing with that. And the graph that I have down here, in order to deal with the absolute value of 1 over the square root of x, is a green one, and that's shown down here, and that is y equal minus 1 over the square root of x. So you see, we start by saying, well, if epsilon is greater than 0, then we can say that this absolute value is less than or equal to this. And you see, it's not always true, but it is true whenever x is bigger than or equal to 2. Those absolute values are true, and think through that, please. So you see, we can say that, well, if we have this then, so this is ln of x over x minus 0 is less than the absolute value of that, and when this is positive I get epsilon, then we know that we can take the square root of x, we can take x to be bigger than 1 over epsilon squared. And so when we do that, and we make sure that m is either bigger than that number or 1/2, then we will always have that inequality. And that means that the absolute value of what we were seeking is less than epsilon, and that means that the limit is equal to 0. Cool, huh? In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. God bless you all. Look forward to seeing you in class.